In this video, I'm going to guide you step by step on how to use the I4I Pitting Corrosion Screening Tool for API 579 Part 6. The link to the tool is in the video description, and this video is meant to be used together with the tool. API 579 Part 6 exists because pitting is not the same as general thinning or a single local thin area. In refineries, pitting shows up in very specific places: cooling water circuits, sour water systems, wet H2S environments, overhead systems where water condenses, and under insulation where moisture gets trapped. The problem is that pitting can look small but still control leak tightness and remaining strength. Because one deep pit can leave a very thin ligament and create a pinhole leak with little warning, Part 6 gives you structured screening paths so you can decide whether a Level 1 pit chart approach is appropriate, whether you need Level 2 pit couple methods, or whether limitations push you to a Level 3 evaluation. Before we start, I want to define a few Part 6 ideas in a simple way. Widespread pitting means lots of pits scattered across a region. Localized pitting means a dense cluster or hotspot that can behave like a local thin area. Arrested pitting means you have evidence the pits are not growing anymore. Active pitting means you cannot justify that it has stopped, so you must consider future growth when you evaluate acceptability. And one more important point. Part 6 uses future corrosion allowance for the region, but you do not subtract allowance from pit depth. You keep pit geometry as measured or projected, and you apply future allowance correctly to the future wall thickness basis. Now here is how to use the I4I screening tool. You will answer every question from 1 through 30 by selecting yes, no, or NA. Use NA only when the question truly does not apply to your component or your objective. Do not use NA because you are unsure. If you are unsure, that is a sign you need more inspection data or better documentation before you can confidently screen the equipment. After you answer all questions, click the button that says check if FFS is needed. The tool will give you a result and it will tell you whether you should proceed with a formal Part 6 assessment. Now let's go question by question with refinery equipment examples so the logic is clear without dragging the runtime longer. Question 1 asks if inspection identified pitting corrosion on a pressure boundary surface that could affect strength or leak tightness. A realistic refinery example is a sour water stripper overhead condenser channel head with scattered pits on the water wet side, or a reflux drum boot where water sits and pits form along the bottom. If pits exist and could reduce remaining ligament, select yes. The question 2 asks if the damage is truly pits rather than broad thinning that should be handled by Part 4 or Part 5. A refinery example of not pitting is FCC main fractionator overhead line CUI, where the wall loss is a smooth band over a large area. A refinery example of true pitting is the cooling water return header, showing discrete cavities scattered across the surface. If it's pits, select yes. If it's broad thinning, select no. Now we classify what kind of pitting case it is. Question 3 asks if pitting is widespread over a region rather than a tight cluster. A refinery example is the sour water stripper column shell course in the water wet zone, showing pits spread over a wide area with no single hotspot controlling. If it's spread out, select yes. The question 4 asks if pitting is localized as a dense cluster that may behave like an LTA. A refinery example is a cluster near the crude unit overhead accumulator nozzle where water condenses and runs down, creating a small footprint with many deep pits. If it behaves like a thin patch, select yes. The question 5 asks if there is also a local thin area present in addition to pits, meaning you have broader thinning and pits inside it, or widespread pitting with one area meeting LTA definition. A refinery example is CUI on a wet gas line elbow where you have a general thinned patch under insulation, and inside that patch there are deeper pits. If you have both behaviors, select yes. The question 6 asks if you are evaluating a blister array as equivalent pitting. A refinery example is a high-pressure separator in wet H2S service, where inspection reports a blister array and you choose to evaluate the weakening effect using Part 6 concepts. If that's your case, select yes. Now we look at applicability limitations for Level 1 and Level 2. The question 7 asks if the component is type A, designed to a recognized code, and internal pressure is the primary load case. A refinery example is a straight shell region on an ASME Section 8 debutanizer reflux drum or a straight run of B31.3 amine circulation piping where internal pressure dominates. If your loads are simple and code basis is known, select yes. If design basis is unknown or loads are unusual, select no. The question 8 asks if the pitting is on only one surface, not both. A refinery example is internal pitting only on a sour water stripper overhead line with clean external condition, or external pitting only on a diesel rundown line under insulation with clean internal service. If pits are significant on both ID and OD, select no, because that pushes you out of simple screening. The question 9 asks if the stress state is membrane dominated, not bending dominated. A refinery example of membrane dominated is a straight section of vacuum tower overhead, piping away from supports and nozzles. A bending dominated example is pitting near a pipe support on a heavy exchanger outlet line where sustained weight and thermal growth produce bending. If bending dominates, select no. Now, the biggest fork in Part 6, arrested versus active pitting. The question 10 asks if you can justify the pitting is arrested for Level 1 screening intent. A refinery example is a cooling water exchanger channel head where the densest region was mapped last turnaround and remapped this turnaround with the same max pit depth and no increase in pit density. If you can defend not growing, select yes. Question 11 asks if pitting is active, are you prepared to assess acceptability at a future inspection date using assumed progression rates? A refinery example is the crude unit overhead accumulator boot where chemistry is variable and you cannot prove arrest, so you run cases for future dates using plausible pit growth rates. If you are prepared to do that, select yes. If not, select no. Now, future corrosion allowance handling. The question 12 asks if you have or can justify future corrosion allowance for the pitting region. A refinery example is using corrosion rate trending from the amine regenerator overhead line to justify future region loss to next inspection. If you have a defensible future allowance, select yes. The question 13 asks if you apply future corrosion allowance correctly and do not subtract it from pit depth. A refinery example is you keep measured pit depth from the sour water stripper overhead condenser as is, and apply allowance to the future remaining thickness basis instead. If you're doing that correctly, select yes. Now Level 1, Data Readiness for Pit Chart Screening. The question 14 asks if you identified the most severely pitted area and documented it with photos and scale or rubbings for pit chart comparison. A refinery example is an inspector boxes the densest region on a cooling water return header spool, photographs it with a ruler, and uses that for chart matching. If you have that, select yes. The question 15 asks if you have a defensible maximum pit depth and minimum thickness at the deepest pit. A refinery example is measuring maximum pit depth on the crude unit overhead accumulator shell in the water wet zone using a pit gauge or UT profiling and documenting the minimum ligament. If you have defensible sizing, select yes. Now the guardrail against pinhole leakage. Question 16 asks if minimum thickness satisfies the minimum thickness limitation intended to prevent pinhole leakage, noting piping and vessels or tanks differ. A refinery example is thin wall cooling water piping where one deep pit can create a leak long before global strength is an issue. If you are below the guardrail, select no and expect escalation. Now, pit chart applicability. The question 17 asks if you can match your observed pitting to a standard pit chart. A refinery example is comparing the pitted surface photo from a sour water stripper reflux line spool to the chart patterns and selecting a close match. If you can match a chart confidently, select yes. If not, select no. The question 18 asks if pitting is more severe than the worst chart. A refinery example is an extremely dense pitted field on a cooling water exchanger channel head where the surface damage exceeds the chart range. If it's beyond chart range, select yes. Now the interaction between pitting and local thin area behavior. Question 19 asks if any single pit is large or deep enough that it effectively behaves like a local thin area and triggers local metal loss style evaluation. A refinery example is one deep pit in a sour water stripper overhead line elbow that dominates the remaining ligament in a small footprint. If that's credible, select yes. Now level 2 pit couple readiness. Question 20 asks if level 2 is required because charts don't fit, pitting isn't arrested, it's localized, or it interacts with an LTA. A refinery example is a localized hotspot on a debutanizer overhead condenser outlet line where chart matching is poor and growth is uncertain. If those conditions apply, select yes. The question 21 asks if you have pit couple measurements for controlling pairs, diameters, depths, and spacing. A refinery example is identifying the controlling pit pair on a cooling water header where two close pits leave the smallest ligament and measuring both pits and their spacing. If you have those measurements, select yes. The question 22 asks if you know pit couple orientation relative to the stress field. A refinery example is on a cylindrical shell like a reflux drum where you identify whether the pit pair aligns more with the hoop stress direction or longitudinal direction. If you're using that refinement and have orientation data, select yes. Now we identify when level 3 is needed. The question 23 asks if you need level 3 because level 1 and 2 do not apply, fail due to limitations, or are overly conservative. A refinery example is both-sided pitting on a thin wall line under insulation where internal pitting exists and external CUI pitting is also present, or pitting at a support saddle region on a horizontal drum where bending stress is significant. If that's your case, select yes. Now objectives, re-rating and remaining life. The question 24 asks if your objective is acceptability and possibly reduced rating like maximum allowable working pressure reduced or MAWPR and maximum fill height reduced or MFHR at coincident temperature. A refinery example is re-rating a sour water stripper overhead condenser to a reduced MAWPR to keep running safely until turnaround. If that's your objective, select yes. The question 25 asks if you also want remaining life using a maximum allowable working pressure based approach. A refinery example is projecting when maximum allowable working pressure reduced for a cooling water return header will drop below required operating pressure as pit depth and density progress. If you need remaining life, select yes. Now we close with inspection quality, documentation, monitoring, and mitigation. The question 26 asks if your inspection methods can reliably characterize pit depth, diameter, and spacing for the selected level, and you validated the data quality. A refinery example is validating measurements on representative pits in a cooling water exchanger channel head and confirming repeatability. If data quality is defensible, select Yes. The question 27 asks if you have complete documentation, location maps, measurements, photos, dates, and operating history. A refinery example is storing the mapped pitting region on a sour water stripper overhead line with dates, measurements, and interval conditions. If documentation is complete, select Yes. The question 28 asks if you planned monitoring when pitting is active or uncertain. A refinery example is setting a shorter re-inspection interval for the crude unit overhead accumulator boot and repeating the same mapped region measurements so you can confirm progression. If you have a monitoring plan, select Yes. The question 29 asks if you considered remediation actions if screening indicates unacceptable damage. A refinery example is planning repair or replacement of a cooling water header spool, plus mitigation like coatings, chemistry control, improved drainage, or inhibitor programs to reduce pitting recurrence. If you've considered remediation, select Yes. The question 30 is the final gate. Based on your answers, do you need a formal Part 6 assessment to justify continued operation or re-rating? In practice, any missing required data, inability to match pit charts, active pitting without a future date plan, both-sided pitting, bending-dominated stress, or interaction with an LTA means you should proceed with formal assessment rather than assuming it is acceptable. If those conditions apply, select Yes. Now let's talk about what the final result means. If the tool indicates that an API 579 Part 6 fitness for service evaluation is likely needed, it means your answers show credible conditions where pitting could control leak tightness or strength, or where limitations push you beyond simple screening. That is where you proceed with the appropriate Level 1, Level 2, or Level 3 method, define the controlling region, and establish acceptability and possibly reduced rating. If the tool indicates that a formal Part 6 assessment may not be required, it means you did not trigger those conditions based on your current information. But it does not mean the equipment is safe forever. If process conditions change, if pitting becomes active, if inspection shows increasing depth or density, or if you plan re-rating or extended run length, rerun the screening. Let me close with the most important takeaway. This tool helps you avoid dismissing pitting as just small holes. It forces you to classify the pitting correctly, confirm whether Level 1 charts apply or whether you need Level 2 or Level 3, confirm whether the pitting is arrested or active, confirm data quality, and confirm you have a defensible monitoring and mitigation plan. Used correctly, it becomes a practical, repeatable gate that tells you when it is time to do the deeper engineering work before you continue operating, re-rate, or defer repairs.